Welcome back. I'm Chris Sikora, and I'm going to step you through week 4 of metallurgy. This week, we're going to take a look at, first of all, we'll go through chapter 4, what it's all about. And basically, it's material properties. So explaining the relationship between hardness, ductility, and strength. Also, we're going to talk about the 7 stresses and material properties. Okay, so 3 primary mechanical properties. First of all, hardness. It's the measure of resistance to penetration. Ductility, I put down the opposite of brittle. So basically, it's where something is like flexible or rubbery. Okay, when it comes to steel, it's just pliable. Okay. And then strength is the measure of how well a material can resist being deformed from its original shape. So some people get hardness and strength mixed up. Like, well, what's the difference? Well, think about it. Hardness is a measurement of resistance to penetration. So how hard, how much force it takes to penetrate that. Whereas strength is how well a material can resist being deformed from its original shape. So it's a little bit different. And we'll talk about that. All right, so hardness. Generally, as strength and hardness increase, ductility decreases and becomes brittle. So there you go. Glass is very hard, but it's very brittle. You drop it on the ground, it shatters. So that's not very strong, if we think about it that way. Okay. A variety of alloys can be added to increase hardness. So when it comes to steel, we're going to see some of those additives. For your midterm, I'm going to ask you to actually put on your little chef hat for cooking metal. So we're going to learn how to sprinkle in this or sprinkle in that to give it different properties. So like, for example, adding lead makes steel more machinable because it actually acts as like a lubricant when you're drilling into it or if you're cutting it. You know, if you want to make it heat resistant, you could add tungsten, which is a very resistant metal. Like, for example, steel melts at around just below 2,000 degrees Fahrenheit, whereas like a metal like tungsten, you're looking at almost 5,000 degrees Fahrenheit. So you add some of that, and it will take the characteristics of that, and depending upon how much you add, you can make it very resistant. So, all right. So let's talk about ductile versus brittle. So ductile is right there you see. Now if you're pulling this apart, like if you had a rod of steel or any material and you're pulling it apart like this, okay, what you get with a ductile is that it actually creates a neck. It gets thin, kind of like bubble gum. If you ever chewed bubble gum and you pull it apart, it gets really thin, okay? Whereas a brittle, it's like chalk. Like, if, I don't know if we don't really have chalk in the classroom these days, but if you try to pull it apart, it's very, very brittle. Just snaps. Doesn't stretch. Okay, so strength, how material reacts to type of load. Now here we have the 7, now this is the 7 loads that we're going to look at. Tensile, compressive. Now compressive, you can see here, for some reason I don't have a good, tensile basically you could test by pulling them. Compressive is the opposite. Oh, there we go. Okay, there we go. On the 2 bolts, you can see to the right tension load, or that's a tensile load. So you see it's actually being pulled apart. Whereas the compressive, it's being smushed together. Okay. Shear. Shear occurs when, like, let's say you have 2 materials that are bound together, and now they could be welded together. In this case, we have a bolt, and the shear is when they're being pulled apart, and so basically it's being ripped from the segment. Whatever, like if there's a weld there, the weld is being taken probably from one side to the other. If there's a bolt, of course, the bolt is acting as almost like a tool ripping it apart. Okay, torsional. And torsional is just twisting it. Now I'm going to put some links to some videos for all of these different ones. They're just short little videos on showing you what these do. Unfortunately, when I make a video, it's not right for me to take and put other people's videos in my video for you to see. So I now have to leave those out. But back in when I would teach this as a class in a classroom, we would just be clicking on links and I would be showing you these videos. So it makes it a little bit less interesting when we can't talk about it. That's why also you'll notice that these, I only go for, like, I think the longest video here is about an hour that we've had so far. And that's usually because we have discussions in class. But that's why I'm giving you the questions at the end of this, at the end of every video, as well as watch these little videos too, because that adds value to it. The whole idea here is I want to help you guys understand these. So when you get out in industry, you understand what an engineer is talking about, or you could understand, like, oh, I ought not to weld it that way, or, you know, the do's and don'ts. Okay, so torsional is like twisting. Okay. Flexural. This one, there's a great little video that you're going to have to watch. Again, I can't really play it, although this one, I think I might be able to actually play this one because it's a short segment. Actually, I think we should be fine. I could play some of it. I will have a link to the whole video if you want, but let's go ahead and give it a try here.
Plane would be destroyed.
So this is the Boeing 777.
The 777 wings could survive the strongest forces that turbulence or bad handling could produce. They were also interested in whether the same wing design could be.
So basically, what you see here is the wings have these cables attached to them, and they're testing. This was actually the first computer simulated aircraft, 100% designed on computer aided design and simulated. So they wanted to see how far they could flex these wings before they broke. And with the simulations and the calculations they did, they got like almost right on target. And here you can see it's bending. And I'll turn it up right before it breaks. Okay, so basically, if you want to watch the rest of it, it's just Boeing 777 wing test on YouTube. But that's a flexural test, and there you can see the force and the sample. Now, even though force shows in that little image in the center, what they were doing, they were actually pulling the wings up, and then that was locked down. It was fixed at the center fuselage. So essentially getting the same type of deal. Okay, then there's fatigue. That's what number of cycles over time, how much stress. We see this with a lot of things. That's why things don't last forever. They eventually get worked enough and they break. If you ever took a pop can, and when you pull that top, you just keep doing that, like what, maybe 10 times, moving the actual clip, and it'll eventually break off. And then impact. All right, so these ones will be on the midterm exam, okay? And so just remember that when you get the midterm. That's a lot. Almost all of these questions, there's a wide variety of them that are actually on midterm and the final exam. Okay, so then we talk about the elastic and plastic range, stress and strain diagram. So for example, the elastic limit is when a material is stressed slightly beyond its proportional limit. If the material is stressed beyond this point, it will not return to its original shape. So that's when they talk about linear behavior. So we could see here there's elastic behavior and plastic behavior, and the elastic limit is that point there. That's what we call yield. When you start doing computer simulation, and had we had this in class, we might have actually did one or two simulations with metal parts to see what happens on a computer when you set them up. But we work with something that's called megapascals. And I want to share with you, now this is out of one of my other classes, a little segment that I think you'll find interesting. This is our CAD 208 class. And we talk about yield, and it's how we read it with the SI units. SI units is for basically scientific use, and it's metric, essentially. And we read it as MPa or megapascals. Now, the point of yield, you can kind of see this is very similar to that chart we just saw in our PowerPoint. Like, for example, human bone has a measurement when it hits that yield point of 130. Now, what that means is it doesn't necessarily, yield doesn't mean that when it breaks, like you saw catastrophic failure with the wing, that doesn't always occur. Sometimes things just bend. Like, see the bolt at the bottom? Sometimes they just bend. But we call it failure, because it's no good to us anymore once the bolt bends. But then there's fracture to the right there, and that's way over here, okay? And dependent upon the material, that band could be different, but you can see here's elastic behavior right here, and there's plastic behavior right there. Now, looking at these different things, look at this. Human bone is about 130, and that's when it yields. Now, in a child, of course, it's like you have green stick fractures, so it's actually bending. Whereas with an adult bone or an elderly person, it breaks because there's not as much flexibility or ductility, you might say. But aluminum, 1060, a very common aluminum alloy, it's one of the more basic ones, it's one of the softer ones, is about 27 to 32 megapascals. So you've all seen an aluminum can, how flexible that is, okay? Then steel. Steel is anywhere between 200 to 700 megapascals. And that depends on additives. So like if you make it into an alloy and you add some different materials, you can make it stronger. And also the way you heat treat it. So if you actually heat treat it and then quench it quickly, it's going to become very hard. And you could get it with combinations of those things. You could get it up to 700 with the right materials added to it to make it an alloy. Okay, so titanium, we see it starts at about 900, and that could get up higher. Like I've seen up to 1500. I think you could get maybe higher than that. Again, with titanium alloy, as they add additional ingredients, they can make it harder, and also different processing. Then there's Kevlar, body armor that you've all seen the police wear it, and the troops wear it. And so that's a Kevlar. It's a weave. It's almost like a polymer. And it's 2,500 to 3,500, depending upon the manufacturer. It could vary a bit. And then finally, carbon fiber. And we see that on cars. We see airplanes, like especially the stealth aircraft that we see. Some of them have carbon fiber components. And supercars have carbon fiber brakes and things like that. So it's very strong at 5,000 or 5,500. I've seen it up to. Now, for the longest time, that's what we had. Like, you know, like some of the stealth aircraft, the 117 stealth aircraft, I think was carbon fiber. Some of it was, and that was developed back in the 80s. Like even they started developing that in the 70s. So carbon fiber has been a long time, been around for a long time. It's just that we're only starting to see it really in use in cars finally in the past decade. Well, anyhow, the past decade has also brought us some new things. Nanotechnology. Okay, nanotechnology is the study of very, very, very small objects. Like imagine making micro gears that can make tiny little robots that float through your bloodstream that could deliver medicine directly to cancer to destroy it. So there's amazing things going on with nanotechnology. But there's also nanotechnology, which is a material science. Now, there's something called carbon nanotubes. And carbon nanotubes are able to synthesize. Now, what's fascinating is carbon nanotubes, they're discovering them in swords. Like you're going to see a documentary on the Umfbert sword. And they have Madagascan steel that is related to, they believe. And what they're discovering now, looking closer, it has what's called carbon nanotubes in it. And carbon nanotubes, it was my understanding, between 4,000 and 8,000 degrees Fahrenheit you have to get whatever material up to that, almost like plasma levels, to synthesize carbon nanotubes, which are basically strings of carbon arranged in a way. And they're these little tiny strands, microscopic strands. Well, anyway, they were discovering that these were in these legendary swords, especially the Umfert. The Umfert, which we're going to see the video very soon on, basically was a sword 1,000 years ahead of its time for the area, for Scandinavia. And whenever whoever had these swords went into battle, they were thought of as this like godly swords because they didn't break in battle, whereas the other swords were breaking, and they were notoriously bad steel, where these were way ahead of their time. So they're discovering carbon nanotubes in Madagascan steel, which is related to that steel used in the Umfert, at least they believe. Now, we're able to synthesize this with microscopic 3D printers, basically, where we could print out molecule by molecule this, and they're taking and interleaving different types of atoms together. Like, so you'll have a lot of carbon, and in between a couple carbon atoms, you'll have a boron atom, for example. Boron, another mineral. Basically, they're finding that that makes a super strong, almost like fabric-like bulletproof material. So it's just fascinating. And look at that, 55,000 megapascals. Remember, bone is about 130. Bone is pretty darn strong. But 55,000 megapascals, you're talking almost science fiction numbers with this. But they're making these things. And as far as I know, they're making them small little segments. Military applications might have more than that. I don't know. But there's another one that's even higher, and it's graphene, again using carbon or graphite. Now this, they've learned that they could actually synthesize this pretty easily, like in a science class, by taking a lead pencil, scribbling it on paper. Then you take cellophane tape, Scotch tape, you put it down, and if you peel it gently enough, you'll take one layer of molecules off of that grouping of carbon. And then what you do, you sandwich them back together somehow using an adhesive. And they can make very strong stuff. There's some videos, I'll try and post one of them, where a person has a knife made of this material, and the knife cuts through ice like a regular knife would cut through butter, as if the knife is hot, just slices through it. It's fascinating stuff. And what, in fact, it's not that it's that sharp, it's that when she's holding it, the heat is transferring instantaneously to the actual blade and melting that steel. So it's just fascinating stuff. And also you can see 65,000 megapascals strength. Unbelievable strength we're talking. A recent article I read, though, they've kind of backpedaled on that a bit. They said, well, in small segments, they found when they tested it was 65,000. But once they were trying to manufacture it in larger scale, it went down significantly. So it fractures easier than they thought. I think science will be able to fix that one day, but we'll see. But carbon nanotubes, definitely really cool stuff. That's science fiction. It's just been around for the past decade, so it's really kind of new. All right, then there's factors of safety, or FOS. If you ever see this, these are numbers given that a computer can generate actually when testing or analyzing a particular part that's designed with the material. And you'll see like automotive uses a spec of 3, and it's basically, to make it in layman terms, it's kind of like 3 times stronger than the base, what you would want. So it's for extra safety. Automotive uses 3.0 for a factor of safety, whereas aerospace uses 1.5. And the reason being is, think of it this way, if you're designing something much thicker and stronger, like for an automobile, so if there's an accident, you're hoping to save lives. In aerospace, especially for rockets and satellite launches, they're not as concerned. They still want safety, of course, but they want to make it lighter so it could be more efficient as it's flying. So 1.5 you might see for that. And civil engineer, it could vary, but I've seen maybe 2.0 for that one. But anyhow, you don't need to know that, but I was just sharing some of this with you because it's really fascinating stuff. If you're interested, CAD 208, you could take this course, and I don't believe there's any, by the time you're in this, I'm not sure what the prerequisite is. There might be a prerequisite, but I don't think there is. Okay, anyhow, let's go back to our PowerPoint here. Okay, so the plastic range is beyond the elastic limit. Deformation grows more rapidly, and essentially at that point, it could break or fracture, or rupture. Okay, and they call it plastic range. Even if it's steel, they're going to call it the plastic range. So just be aware, it's not related to actually polymer material, okay? Okay, then there's something called creep. It's when a material is loaded and sustained for a long period of time. This phenomena happens where essentially the flow of the material occurs and it will actually stretch it. Now, one of the neatest things I've seen, and I have been able to find on YouTube again, was glass that was made back in the 1700s that was on like old buildings and structures. And what happens is they were looking at the glass, and the panes of glass, instead of being straight, were like angled. And what they said was happening is it slowly was creeping down, and the material was transferring over the 200 years that it's been around. So that can happen. It could also, like if you have a line of material like a metal and you're pulling it apart, it'll gradually get thinner as it's pulling apart, and it can fracture. Okay, Poisson's ratio, there is an equation here, and I do ask you just for the equation. You can see Poisson's ratio is equal to lateral strain over axial strain. This is as far as we go when it comes to equations. I don't actually have you put it in. This isn't a book for this isn't a class intended for engineers. It's more for technicians, welders, and manufacturing people. So I'm not going to test you on any equations or anything like that, so don't worry. But I would like you to have, when I say what is Poisson's ratio, just put that equal to lateral versus over axial. Okay, so it's when a material is strained and elongated in one direction, the material decreases in size in the other. So here we have this box, all right? And as it gets pulled, you can see it gets longer, but look at how it gets thinner here. Now as it gets compressed, it actually gets thicker. So each material behaves differently, and this is actually measured by scientists. And whenever you get a material, you could actually look up what Poisson's ratio is, so you know how flexible or what's going to happen. How is it going to behave? All right, so chemical properties. This one, a lot of people get it wrong on the midterm. And all I'm asking you for is what you see down there, rust. Okay, corrosion, one of the most important factors of selecting material. Okay, so we want to make sure it doesn't rust too quickly. Oxidation is a chemical reaction between the material and oxygen, aka rust. So that's literally on the test. I'm going to say oxidation is a chemical reaction between the material. This is just copied and pasted in my test. I'm not kidding. But I'm going to ask you, what is it? What's another name for it? Just give me rust or corrosion. Or, actually, I don't even have oxidation. That's right. Oxidation could be one of the answers. It is blank is a chemical reaction between the material and oxygen. So what I'm looking for is oxidation. And oxidation occurs with other things other than just steel, too. Be aware it occurs with plastics. It occurs with metals. You see it quite often over time. It's just Mother Nature breaking down things. I don't like to use Mother Nature because this is a science course. Technically, we don't say Mother Nature. But essentially, it's how oxygen gets into things and starts breaking it down. Oxygen, we breathe it, but it does damage to things. It breaks stuff down. Okay. All right, additional properties for consideration. Electrical, magnetic, thermal, weight, wear, machinability, weldability. So there's a comparison on page 66 of all these properties of your book. You guys have to read it anyway, so just go through it, know where it's at. This book is actually a nice book to just keep. If you want to return it, by all means, go for it. But those of you in welding or in manufacturing, it is good for these types of things that it has. You could Google a lot of this stuff now, but the book has it in a nice, clear format. It's easy to find. So, when you're looking at selecting a material for something, you have to think about it. Like, is it a good electrical conductor or is it not? Like aluminum, when we talk about aluminum, it's actually a fantastic electrical conductor, but you don't ever see it. Used to be used in electrical lines in your house, but they took it out. And the reason being, some of you might know this already, it's because it melts. It has a low melting point. And what happens with a short circuit? I mean, wires get hot. Sometimes you guys have done it when you've had an electric heater running. Touch that cable, it's going to get really hot. So they still do use it for the big power lines that you see, those big ones. But anyhow, magnetic. Do you want something that's non-magnetic? Okay. At one point, I was designing what was called a portacath for my son, Michael. My son had cancer a number of years ago, and most people who get cancer get this thing put in their chest. It's called a portacath or a port, and it goes underneath the skin. It's just, think of a little tiny cup the size of a quarter, maybe that thick, and it has a rubber diaphragm over it. Okay, self-sealing rubber, and it has a little line going out, goes right into a vein that goes into your heart. And then it goes, they implant it just under the skin. Okay, so then you could put a needle in, and it's just like filling the tank on of gas on your car. It's an easy access point, because normally if you're accessing veins and arteries with needles, you don't want to keep doing that. Put in a port, and they do this for cancer patients because they give you so many different drugs and things like that. Well, anyway, my son was being fed through that too, rather than because he couldn't eat. He had a tumor in his neck. And I was working with doctors to make this port to where it's self-sterilized. Now, what's fascinating, metals can be sterilizers too. Copper has properties to actually kills COVID 3 times faster than it being on any other material, if it's on copper. Also silver. Some of you might have heard the old adage, that person was born with a silver spoon in their mouth when they refer to someone wealthy. Well, that's because silver spoons back in the day, before they had detergents and hot water easily accessible, when you would just wipe your silverware off and you'd put it away. We're talking like 1800s, you didn't have the ability to wash it all the time. Well, guess what? Just wiping it off, there's still traces of that food, your saliva. Bacteria loves that, grows on it. Well, what they found out early on is that if it was a silver spoon or silverware, that bacteria couldn't grow on it. And so people who ate with silver spoons wouldn't get sick as often, so they were privileged. So there's all these really neat and fascinating things. But anyway, going back to my port, I thought about making it silver on the inside, but there's issues with that, especially if there's blood going in and out. But I ended up putting a little ultraviolet light bulb inside of it, and the ultraviolet light at a specific frequency, it's UVC. UVC never even reaches the earth because it could kill everything. If it did, it kills 99.9% of everything. So anyway, when I designed this, one of the problems is I didn't want it to have an effect, because a lot of cancer patients have, they get MRIs, magnetic resonance tracings. So a magnetic metal would actually, if you had to get an MRI again, the MRI would actually rip it right out of his chest, and he'd probably bleed to death. But so I was working with some people on trying to make that non-magnetic and looking at different metals and things like that. So a lot of really neat stuff. I'm sorry I got off on a tangent there, but there's some really fascinating stuff when it comes to metals. Okay, and so your assignment for next week, read chapter 5, do questions 1 through 10, 17, and 25. They're on page 87 of your book. Week 4 video questions. So get these to me. The Boeing 777 aircraft wing video. This is all referring to. So answer the questions here. Which of the 7 stresses was applied? Okay, we talked about that. You could always go back and review the video. What percentage overload did they achieve? It's caught in there. If you watch the video even that I recorded, it's actually in there. You could hear in the background a guy is actually saying it. Okay, if not, just go to the YouTube and watch the whole video. Okay, and then what is aircraft aluminum? I want you to Google it. Okay, just type in Google aircraft aluminum. Just give me the little paragraph that they give you, the first little paragraph. You don't have to go in big detail. Okay, so those are your questions to get to me, okay? Again, those of you who are procrastinators, if you're getting this late, hey, talk to me, it's okay. My wife's a procrastinator, as I think I told you guys. She's fantastic at her job. And so it's okay if you're a procrastinator, especially in this COVID era. In real life, of course, you don't want to be that way, like working for a company, unless they're okay with that. But that's about it. That concludes this. And I will see you guys next week. Have a good one.